Perfect.
Okay, great. Okay, so first of all, thank you everyone for being here, and it's my pleasure to introduce Mr. Romualdi for his PhD presentation. Connected from around the world, we have the jury members and reviewers. Reviewers are Marco Uter and Jerry Pratt. And then, in addition to these two reviewers, we have also Johannes Anglesberger and Alexander Leonessa. So, Mr. Romualdi has about 45 minutes to present his work over the last 3 years carried out for this PhD.
Okay, so I hope that you can see the screen. Can you confirm it, please?
Yes. Yeah, I can see the screen.
Okay, perfect. So good afternoon, everybody. I'm Giulio Romualdi, a PhD candidate at the Italian Institute of Technology, and today I will present you the activity that I carry on during my PhD. So first of all, I would like to thank my supervisor, my co-advisor, the thesis committee, and family and friends that are attending this presentation. So this thesis, the title of the thesis is Online Control of Humanoid Robot Locomotion, and then I will present you some different strategies in order to achieve humanoid robot locomotion in different kind of environment. So before entering into the technical details, I would like to present two examples where humanoid robots in general locomotion play a crucial role. So we are living in an area characterized by disaster scenarios, and every day the human being has to face with fire, flood, earthquake, and in this context, an experienced worker can help. But unfortunately, the human beings are not allowed to operate safely due to the hazardous situation and condition of the environment. As a second example, let's now imagine the worker of the future. According to the statistics, back injuries account for 1 in every 5 injuries and illness in the workplace. And this is due to the manual handling of loads. So as a robotic researcher, in which way we can improve the working condition for a human? Well, a possible solution is to use humanoid robots. Why? Because in this respect, a humanoid robot can help the worker of the future in accomplish the everyday task, or thanks to teleexistence, can help a person to live in another place. And in this context, the locomotion capability in different kind of environment becomes crucial to allow the robot to safely interact with the environment and with other humans. So the high-level question is how to design control strategy that allows a human robot to work in a human-like environment. Well, we are not the first one that you try to answer this question. And as you know better than me, during the DARPA Robotics Challenge, several researchers tried to design controller architecture to allow a humanoid robot to perform tasks in a disaster scenario. One of the main outcomes of the DARPA Robotics Challenge is the controller architecture. So in this case, we propose, I will show you a 3-layer controller architecture where the full-step planner is in charge to generate the full-step position and timings. The receding horizon controller in general assumes simplified model for the humanoid robot and stabilize the robot dynamics. And finally, a whole body controller guarantees the tracking of the Cartesian task, changing the position and the velocity of the joints. Finally, we have a perception layer, and this perception layer gathers all the data coming from the robot, the vision, the data, and provides the feedback for the control loops. It's important to notice that the inner is the loop, the higher is the frequency at which the block runs. And in general, a full-step planner runs a lower frequency than a whole body controller. At the same time, inner is the loop and higher is the model complexity. So this means that a receding horizon controller runs in general a lower frequency with a low model complexity, and this allows the researcher to implement an optimal control strategy or MPC strategies. Okay, so the research question is this one. Is it possible to consider a 3-layer controller architecture and change the implementation of each block? So the main idea is that we believe that different kind of tasks can be performed while preserving the cascade controller architecture, but modifying the model considered inside. So the thesis contributes toward this aspect here. I will first start with a benchmarking of simplified model-based architecture, and then we try to remove some assumption of the controller in this kind of test. So we have a whole body controller for humanoid robot in viscoelastic environment. Then we remove the assumption of rigid links. And finally, I will present you a nonlinear centroidal MPC with step adjustment capabilities. So this is the presentation outline. I will start with a short background. Then I will present you the benchmarking. Later on, I will show you how we have to change the whole body controller in order to handle elastic contact. I will also present you a whole body controller in case of robot affected with flexible link. And finally, we'll present the nonlinear centroidal MPC. Let's start from the background. As you know, the humanoid robot is a perfect example of a protein-based system, and this means that its configuration is not only described by the joint status, but we also need to know the position of the base. On the right-hand side, there is the dynamics of the system, where M is the mass matrix, H contains the Coriolis and gravitational terms, tau the joint torques, F the contact branches, and J the contact Jacobian. So starting from this equation, we can actually extract the so-called centroidal dynamics, that in the end is just the central mass dynamics and the angular momentum dynamics. And thanks to the Newton law, we know that this centroidal dynamic depends mainly on the contact branches. And here, H dot is the centroidal momentum rate of change, and X is the so-called coadjoint matrix. That is a matrix that allows us to convert a branch expressed in a frame into the centroidal frame. And finally, G bar is the 60 gravity acceleration. So a question here is, can we further simplify this kind of model? And actually the answer is yes, because assuming a constant central mass height and a constant zero angular momentum, the centroidal dynamics can be simplified using the linear inverted pendulum dynamics presented by Kajita. So in this equation, XCOM is the central mass, B is the time constant of the linear inverted pendulum, and XZMP is the zero moment point that plays a crucial role in the contact stability criterion. So the linear inverted pendulum dynamics is linear, but unfortunately is not stable. So one of the ideas is to perform a sort of decomposition thanks to the definition of the DCM that has been proposed back in time by Jerry Pratt and Johannes Engelsberger. And thanks to this new quantity, it's possible to split the linear inverted pendulum dynamics in two parts. The first part is the so-called stable dynamics, and the other part is the unstable dynamics. The stable dynamics shows that the central mass automatically follows the DCM, while the unstable dynamics is often considered inside the control strategy in order to stabilize it. So to recap, the model used across these theses are the following one. So we use the robot dynamics, the full robot dynamics, then the centroidal momentum dynamics, and finally the DCM dynamics. Okay, so now I will present you the benchmarking of a multi-layer controller architecture. This work has been initially submitted and published in Humanoid 2018, and then we extended in a journal paper in 2020. So let's start again from the architecture, the three-layer controller architecture, and now I will change the name of some blocks, and I will explain you why later. So the full step planner becomes the trajectory optimization layer, and this is in charge not only to generate the full step position, but also the DCM trajectory. The receding horizon controller becomes a simplified model controller. And finally, we have the whole body controller. So let's start from the trajectory optimization layer. Here, we assume that the humanoid robot works as a unicycle, and we can do that thanks to the work that Steve Dafarra presented in IROS 2018. And this planner assumes that the robot works as a unicycle, and so we can sample the foot starting from the position of the wheels of the unicycle. When we have the foot position, we implement the Dcm Planner that Engelsberger presented in IROS 2014. And this planner assumes a constant ZMP in case of single support, while for double support, you use a cubic spline. Okay, so we consider the trajectory optimization fixed, so we don't move it, we don't change it anymore, and we focus on the simplified model control layer. So we started from an instantaneous controller. This controller here is composed of two parts. The first blue term is the feedback term, and the red term is the feed-forward term. This controller is super simple to implement, but unfortunately, it has some problem. For instance, the ZMP stability criterion may be violated, so the ZMP may exit the support polygon of the foot. As a solution is to design and implement a predictive controller that is composed of three main ingredients. Of course, we have the DCM dynamics, We have the objective function that consider the DCM tracking and some regularization terms for the ZMP. And finally, the feasibility condition. So in this case, the ZMP will always stay inside the support polygon. Okay, now regarding the whole body controller, we propose two main approaches. The first one is the kinematic approach. The kinematics in the approach, in the end, try to find a robot velocity while minimizing a cost function that is composed by several terms. That is, we have the torso orientation and the regularization terms for the joints. And this optimization problem is subject to a set of constraints. So first of all, we have a central mass constraint tracking and then a fit tracking. Okay, so if the robot is velocity control, the output of this controller can be directly sent to the robot. Otherwise, if the robot emits only position control, the output of this problem can be integrated and then send it to the robot. This control strategy has a problem. The main problem is the fact that we don't consider the forces. So actually, the counter branches can be unfeasible. We now compare the Kinematics architecture, and here there are some labels with predictive and instantaneous, which means that the simplified model controller implements a predictive controller or an instantaneous controller, while position and velocity means that the robot is controlled in position or in velocity. The experiments are carried on the humanoid robot ICAB, and we noticed that when the robot is controlled using an instantaneous controller and in position, we are able to reach highest velocity. Okay, going back to the architecture, we can now focus on the dynamic-based whole body controller. So here, the control problem is a bit more complex. We try to find the robot acceleration, the counter forces, and the joint torques. Still, there is an objective function that where we consider a torque orientation task, a joint regularization task, a force regularization task, and some torque regularization task. And in order to have feasible counter forces, we had constraints for the counter branch feasibility. We consider, of course, the robot dynamics, and then we have some constraints relating to the tracking. So we have the central mass tracking constraint, the fit tracking constraint, and then we consider the joint needs. Okay, this presents on the right-hand side the experiments on the ICAB humanoid robot walking in torque. So as you can see, the walking velocity is really, really lower with respect to the one that we have in case of using instantaneous controller. And this can be also seen on the animation on the left-hand side. And this is actually due to the low-level joint torque tracking. We try to increase the gains, but unfortunately, the noise acting on the noise on the joint torque estimation doesn't allow us to reach the same performances of the instantaneous controller. So in conclusion, we notice that the instantaneous controller and the IK allows to reach the highest velocity. And unfortunately, the high torque control tracking error degrades the overall performances. Then this architecture has two main, let's say, limitations. The first one is that it doesn't consider any kind of push recovery strategy. And the second one is the fact that the contact between the robot and the environment is considered rigid. So these 2 points motivate the research that we are going to present in the next slides. Okay, so now I will present you a whole body controller for locomotion in elastic environment. And this work has been published in the Robotics and Automation Letter. Okay, so when the contact with the robot and the environment is sufficiently stiff, controller based on rigid contact assumption works nicely. However, when the compliance of the environment increases, it is pivotal to design a contact model that identifies the stiffness and damping parameters of the system. This contact model then can be incorporated in a whole body controller architecture. So what we are going to present is a whole body controller for working on a viscoelastic environment. So before entering into the details, I would like to go in a short recap of the state of the art. So one of the possibilities, so the main goal is to design an online controller for working on compliant surface. And one of the main approaches is to design a controller that assumes rigid contact assumption. And actually, there are several papers where passivity-based and robust controller show that a humanoid robot can balance on viscoelastic environment. The other opposite direction is to model the flexibility of the contact. And this can be done using lumped model. So those models in general rely on few parameters, 2 or 4 parameters, and they can be elastic or viscoelastic. So the first one contains model just elasticity of the contact, while the second one model the viscoelasticity. Another approach is using the finite element analysis. And this approach is completely different from lumped model because the performances and the modeling capabilities are higher, but it can be complex to use it online. And actually, the FEM and lumped model has its own pros and cons. So for the lumped model, we know that they can be used online because they are actually really, really simple. In general, they are linear systems. And one of the main problems there is the fact that the foot is often modeled as a point or as a rectangular surface. In the case of rectangular surface, this model, they often rely on rotational spring and damper system, and it's not easy to give a physical meaning to this kind of model, to this kind of system. Then we have the FEM model, and in this case, this kind of approach provides an enhanced capabilities in modeling, but on the other hand, they are computationally heavy. So this prevents actually their use online in real time and time critical application. So our contribution goes in the middle actually. So we want to propose a continuous spring damper system model that should run online, and at the same time, it should not rely on rotational spring and damper system. So the contribution are the following one. We start with the continuum spring damper system model. Then I will present you a whole body controller that uses this kind of model. I will show you a contact parameter estimator, and then we validate the proposed approach in simulation. The code is open source, you can find it on GitHub. Okay, so let's start from a rigid body that is in contact with the environment. And we can assume that for each point in the contact surface, there is an infinitesimal spring and damper system that generates a force. And this force depends on the spring and damper coefficient. And then we have the position of that point, that is x, its velocity, x dot, and x bar, that is the position of the point such that we have a zero velocity in case of zero force in case of zero velocity. So now we can imagine to apply this function to all the points of the contact surface, and what we have in the end is a vector field. So the main idea here is to take this vector field and evaluate the integral of the vector field in the contact domain. Thanks to that, we can compute an equivalent contact branch, so force and torque. It's interesting to notice that this contact branch depends only on the state of the rigid body, so its position, orientation, and velocity, on the contact parameters, and of course on the contact domain. In the paper and also in the chapter of the thesis, I show that in case of rectangular surface, it's pretty simple to find a closed form solution for the model. So I would like to show you why this kind of model, the model that we propose, is actually a generalization of the linear model. So this one is the equation that for a non-linear rotational spring system in the case of a rectangular surface. And then if we compute the small angle approximation, we obtain the so-called rotational spring that is widely used in the literature. So here K, in our case, is the spring parameter. It's important to notice that the spring parameter is actually a matrix that depends on the shape of the contact and on the characteristic of the environment. So thanks to this, we were able to give a physical meaning to the rotational spring. And here, theta is the Euler angle of the approximation. So we can conclude actually that our model is a generalization of the linear model. And since for small angle approximation, the results are actually the same. Okay, so let's go back to the architecture, and now let's focus to the whole body controller. So the whole body controller is actually composed of two blocks. So we have the real whole body controller and a contact parameter estimator. The aim of the whole body controller is to compute the desired joint torque while considering the estimated contact branches and the desired robot acceleration. So in order to compute the desired robot acceleration, we design a block that takes as an input the contact model, the desired fit trajectory, the desired centroidal momentum trajectory, and some regularization terms. The output will be the desired robot acceleration that then are used to compute the desired joint torque. So in the end, inside this block, there is an optimization problem where we try to find the robot acceleration and the contact force rate of change. Here it's important to notice that when we have a viscoelastic environment, it's not possible to directly control the force, since the force depends on the state of the robot. And so we assume that it's possible to control the rate of change of the contact force that actually depends on the robot acceleration. So we have a cost function where we have several terms. The first one is a centroidal momentum tracking task. We have also some regularization terms, one for the torso orientation, the other one for the root link orientation, a swing foot tracking task, and regularization for the joints and for the contact forces. In order to have feasible contact branches, we also have a task for the feasibility. Of course, we consider the robot-based dynamics and the contact dynamics. Okay, so now let's go inside the contact parameter estimator. This actually is required because, as you can imagine, the whole body controller relies on the contact model. And so this contact model depends on the contact parameter. The contact parameter is based on the fact that the model that we propose depends linearly on the spring coefficient and on the damper coefficient. And so in the end, what we implement is a recursively square algorithm that takes as an input the contact model, the state of the foot, and the contact branch. The output is the contact parameters that then are used by the controller in order to generate the joint torques. Okay, so taking again the architecture, regarding the trajectory optimization layer, we use also here the Unicycle Planner proposed by Dafara back in time. And for the simplified model control layer, for the linear momentum, we use the Dcm controller, while for the angular momentum, we evaluated propagating the desired robot kinematics, and we use the centroidal momentum metrics. Okay, so first of all, I would like to present you a comparison of the controller that we propose that is here called TSD compliant, and the so-called TSD rigid, that is the controller of the first part of the presentation. So when the compliance increases, TSD rigid is no more able to find a feasible solution, while TSD compliant, yes, is able to accomplish the task, while the estimator of the contact parameters is running online. And actually, regarding the contact parameter estimator, I also would like to show you the performances. So in order to test the parameter estimator, we design an environment with variable spring and damper coefficients. And as you can see here at the touchdown, there is a spike on the estimated damper coefficient, but still the spring and the damper converges to the real value. And in these experiments, I also add a white Gaussian noise on the contact forces in order to improve to test better the estimation. So in conclusion, we present a model that doesn't rely on any kind of rotational spring and damper. And actually, our model generalized the linear rotation spring damper system. We use this model in a whole body controller for working on compliant terrain. As a future direction, we would like to port this architecture on the real robot. But in order to do that, we need a reliable joint torque controller. And we also need a really good floating-based estimator because we cannot directly use the so-called leg odometry since the position of the stance foot moves while the foot is in contact. Another, let's say, assumption of this controller is the fact that all the links of the robot are rigid. So in the next part of the presentation, I try to remove this hypothesis. And I will present you a whole body controller for locomotion with robot having flexible links. This work has been just submitted in Humanoid 2022 and has been done in collaboration with LAS. And actually, I did this work during my period abroad there under the supervision of Professor Olivier Stas. Okay, so when the link of the robot are sufficiently stiff, so when the link of the robot is sufficiently stiff, controller based on rigid body assumption works fine. However, when the robot is equipped with flexible links, it's crucial to design a controller strategy that considers the link flexibility. So in this part of presentation, I will present you a whole body controller that allows a humanoid robot with flexible link to work in a rigid environment. So the flexibility on the robot is actually something that is not new because this robot here that is called David is a robot of DLR, has a variable stiffness actuator, and thanks to that is able to safely interact with the environment. On the other kind of flexibility is the link flexibility. So regarding the link flexibility, Villa in 2022 notice a link deflection in the cross-section between the root of the Talos robot and its hip. So actually, the state-of-the-art contains several examples of robot having link flexibility. One of the most important is the Kajita paper back in time that consider and models the compliant material in the ankle joint. This model is then used in the controller in order to have a reliable whole body controller for working in a human-like environment. And finally, Villa presents a control strategy in order to handle the flexibility in the cross-section of the hip and the root link of the talus. So this controller has one problem, since all these kind of methods perform a local compensation for the link elasticity. So what we are going to propose is a controller that performs a whole body compensation for the elasticity. Then we will present also a flexible joint state observer, and then a simulation experiments on the Talos humanoid robot. So why flexible joint state observer? Because there are several ways to model the link flexibility, among which the most common one is to take a flexible robot and remove all the flexible links and substitute it with flexible joints. And those flexible joints have dynamics given by a spring and damper, where K is the spring coefficient and D is the damper coefficient. So actually modeling a robot with flexible link is not so different from modeling a robot with rigid link, since the dynamics at the first impression can be exactly the same, but what differs is the content of the variables. So now nu contains not only the base velocity and the actuated joint velocity, but also the flexible link velocity. The same for Q, that now contains the flexible joint position. And now we have also tau-A, that are the actuated joint torques, the one that we can send to the robot, and the flexible joint torques. So in this case, the flexible joint torques implements the law that has been proposed and used by Villa. It's important to notice that if we discretize the flexible joint dynamics, it's possible to write a sort of estimator for the joint position and velocities that depends on the previous state and on the current status of the current torque of the flexible joint. So taking again our architecture, we now consider the whole body controller. The whole body controller also here is composed of two blocks. We have the real whole body controller and a flexible joint state estimator. The whole body controller is again an optimization problem where we try to find the robot acceleration, a contact force, and the actuated joint torques. This optimization problem tries to find the minimum of a cost function that contains a torso regularization task, a root regularization task, and then some joint regularizations. We also had some tracking tasks, high-level tracking, high priority tracking tasks. So we have a foot trajectory tracking task and the centroidal momentum tracking. And then, of course, we consider the whole body robot dynamics and the counterbranch feasibility. So actually, the flexibility of the joint plays here a crucial role in the definition of the multi-body dynamics, since the state of the flexible links and joints actually are inside the multi-body dynamics constraints. So this means that we need an estimator, something that estimates the flexible joint link state, and because otherwise it's not possible to consider it inside the controller. So what we propose is actually a recursive Newtonian algorithm that uses the actuated joint torques and the contact branches. And the output of this algorithm are the flexible joint state. So starting from the torque, then we can use the approximation of the joint position and velocity. And then we can also evaluate the position velocity of the flexible joint. Okay, so now I would like to present you the comparison between the TSD rigid and TSD flex. TSD flex is the controller that I just presented. And as you can see here, when the stiffness parameters is pretty high, TSD rigid is enough. So we don't need to design a controller that considers the elasticity. But unfortunately, this is not true in the case of the elasticity, in the case of a system with links that has a higher elasticity. So here, TSD rigid is not able to perform a step. Why this? Because Well, also the position of the center of mass is not the right position, because the model that is considered inside TSRE rigid assumes a fixed link and all the links and fixed joints, and all the joints are assumed to be actuated. So there is no possibility to add flexible joint there. While TSRE Flex, this is the controller that I just proposed, is still able to perform the task. Okay, so now I would like to present you the capability of the flexible joint estimator. So in this case, on the right-hand side, you can see the plot of the joint position, velocity, and torque, one of the flexible joint. As you can see, every time the foot touches the ground, there is a spike in the estimation. This spike is actually, even if it's there, the controller is still able to complete and perform the locomotion task. Okay, so in conclusion, we designed a whole body controller for robot with flexible link, and then we didn't have to perform any kind of local compensation for the flexibility. We also present a joint state observer, and then as a future work, we would like to test the architecture on the real scenario, so on Talos, and actually compare it with the work of Villa. And then as a possible future direction is to consider the link flexibility directly in the generation of whole body trajectory. So now we can conclude the part related to the whole body control layer. And from now on, we assume that we have a whole body controller able to guarantee the tracking of all the Cartesian quantities, sending, for instance, position directly to the robot. And now we try to improve the simplified model control layer. So how to do that? Well, now I will present you a nonlinear centroidal MPC, and this work has been just presented in the latest cycle. And when a disturbance acts on the robot, it may be necessary to recompute the contact location in order to prevent the robot from falling. And actually, this is not a new topic, because Feng, back in time, in 2016, present simplified model-based strategy in order to adjust the position of the footstep. Then Griffin in 2017 extend this architecture in order to consider also the timing adjustment. And finally, Shafi in 2019 changed the approach proposed by Griffin and Feng in order to consider variable ZMP trajectory during the single support. Simplified models are cool because they can run online. They are easy to deploy on the real hardware, but unfortunately there are some cons. For instance, in Shafi, it is required to design an additional block for enabling the step recovery capabilities. And moreover, these kind of approaches are tailored on a specific task. For instance, if you want to design a controller for running and a controller for locomotion or jumping, you cannot use directly the same simplified model. So this means that we have to somehow connect those kind of models. Another approach is to use a full robot model, and these are in the opposite direction. So in this case, the contact location and timings are generated by considering the entire robot modeling. And here it's worth to mention the work of Dai in 2014, where it was one of the first ones that considered the centroidal dynamics in the generation of the trajectory for a humanoid robot. Then Ponton find a convex relaxation for the angular momentum dynamics. And finally, in Dafara, the interaction between the robot and the walking surface is modeled explicitly via a new kind of condition that are called dynamically complementary constraints. Also, the full robot modeling has its own pros and cons. One of the main pros is the fact that they consider the entire robot specification. So the limits, for instance, we are sure that the trajectory that they are going to generate is feasible in sense of joints limits, for instance. And then they can use to achieve multiple tasks. For instance, the work of Dai, in the work of Dai, the very same approach is used to running, walking, and jumping. But unfortunately, there are some cons. So first of all, it's complex to run them online because the optimization problem that they try to solve is in general huge, and it requires some seconds, sometimes minutes to find a solution. And then it's complex to test it on the real platform because the number of parameters that are required to tune this kind of planners is pretty high. And this, with the fact that testing the controller and running this controller require a lot of time, make it in the end complex to test it on a real platform. So our contribution goes in the middle also here. We want to present a nonlinear centroidal MPC. So we want to move from simplified model, but at the same time, we want to have something that runs online. And then I will also present you some simulation experiments on reduced models. And finally, we deploy our architecture, our controller on the humanoid robot ICAP tree. Also here, the code is public and you can easily find on GitHub. Okay, so let's start from a multi-body system. As you know, when this system interacts with the environment, it's possible to find the dynamics of the system and consider the centroidal dynamics of the system. And the main idea here is to have these centroidal dynamics along with a high-level planner for the footsteps. The high-level planner generates only nominal footsteps, position, and location. The main idea here is to combine these two information in a sort of machine that is and this machine should generate some outputs that are the feasible contact branches, should adjust automatically the position of the footstep, and in general, it will generate feasible central mass trajectory and angular momentum trajectory. In order to implement this controller, we exploit the model predictive controller strategy. This strategy is required three main ingredients. The first ingredient is the prediction model. As a prediction model, we consider the centroidal dynamics. We also have an objective function. So the idea here is to take the output of the footstep planner, and from that we can evaluate with some heuristic the nominal central mass trajectory, nominal force, and nominal contact. And those quantities are used as a regularizer in the MPC. It's important to notice that all those nominal quantities may not be feasible, and since the feasibility is guaranteed by the centroidal MPC itself. And this is done thanks to some constraints that the most important one is the force constraint. So we want that all the branches are inside the branch cone. And also we want that the computed contact is next to the nominal one in a given region. And this is required to consider the kinematics and the limits of the robot. So now I would like to present you a simulation in Matlab. When there is a one-leg robot that is jumping, and at a certain point, an external disturbance acts on the system. So here is important to notice that the controller that we just presented is able to handle aerial phases. Moreover, the controller is able to guarantee the balancing and complete the task, even if there was an external force act on it. And this has been done changing automatically the contact position. In these other experiments, I would like to show you a simulation experiment in Matlab, where we have a two-legs robot that is switching from a locomotion pattern to a running pattern. Also here, there was an external disturbance acting on the robot. So it's important to notice that the controller is automatically able to switch from a locomotion, let's say, task to a running task. And this is done automatically by the controller, generating aerial phases and automatically adjusting the position of the footsteps. We also deploy our controller in the three-layer controller architecture. So here, the whole body controller implements a QP inverse kinematics, and the footstep planner generates just the position of the footsteps. So the robot is controlling position. This means that it behaves rigid when it interacts with the environment or when an external disturbance acts on it. So we try to mitigate this effect in considering the contact forces as a measured disturbance in the centroidal MPC. And this is actually the experiment. So at a certain point, there is an operator pushing the robot, and the MPC automatically adjusts the position of the footstep. So there is no an external block or an external heuristic that is in charge to detect the contact. It's the MPC itself that decides to generate a new contact position, and all this kind of architecture runs online. So in conclusion, we propose an MPC with step recovery capabilities that emerge automatically. The control that we propose generalized on the number of contacts, so it can be used actually also with quadrupeds. And as a future direction, we would like to consider the contact timing adjustment. So the control that we propose adjusts just the position of the footstep. And Finally, it also would be nice to warm start the controller with trajectory-like, human-like trajectory generator, for instance, the one presented by Vice Conte in 2022. So in conclusion, we start from the we start from the three-layer controller architecture. From this three-layer controller architecture, we focus on the whole body control layer. And we start from a whole body controller for working on rigid environment. We remove the rigid environment assumption and we present a whole body controller for viscoelastic environment. And finally, I also remove the rigid link hypothesis. At least for the ICAB humanoid robot, we noticed that when the robot is controlling position, we were able to achieve highest performances, while the low-level joint torque tracking didn't give us the possibility to reach the very same performances of the position control. And moreover, we also noticed that in case of elastic environment, it may be necessary to design a controller that considers the elasticity, and the same for the link flexibility. Regarding the simplified model, we start from a benchmarking of simplified model-based controllers. And one of the main problem of the architecture that we use here was the fact that it was not possible to adjust the position of the first step. So what we propose is a nonlinear centroidal MPC with step adjustment capabilities. And this MPC, even if it is nonlinear, is still able to run online. So at the beginning of this presentation, I mentioned that, in my opinion, the future of the human robotics is the safe interaction between robot and humans in a human-like environment. So the road to achieve this kind of goal is still long, but I hope that the controllers presented in this presentation will help the humankind in the future. So thanks for the attention, and now I'm opening to the question.
Okay, so I don't know if jury members hear us.
Yes, we can hear you.
Yes, can hear you.
And it would be great if you could put the jury members. Let me see them.
Yes. Okay.
Okay, so we start with the question time, and we will start with the PhD thesis reviewers in alphabetical order. So the first one to come to stage is Professor Marco Utter.
All right. Thanks a lot, Giulio. First of all, congratulations for a nice piece of work. Maybe it's good if you could open up your slides again, that we could go through a couple of things that you showed during the presentation with a few questions and then go back to the thesis. So if you could start with the concluding slide that you had, like slide 75 or something like this, I think that would be helpful.
Okay, let me 75.
For example, yes. So you had always the same structure of these three layers.
Oh, okay, okay. You mean the okay.
So first, just out of curiosity, if you have these three layers, could you tell us for your setup that you had it running on the system, what were roughly the frequencies in these three? Yeah, sure. So in the case of simplified models, we use only one thread. So all the application runs at 100 Hertz. So both the whole body controller, the simplified model controller, and the trajectory optimization layer runs in the same process on a computer that is mounted on the head of the robot. And the frequency is 100 Hertz. We are trying to improve the frequencies, and we are working on, let's say, handling the connection between the network infrastructure. So we are currently working to double the frequency from the network communication. Okay, and how was that with the more complex dynamics, if you had the MPC? For the complex dynamics, actually, so this one. Okay, so the MPC in this case runs in a separate thread, and the frequency is 10 Hertz. So that's the reason why we would like to warm start the MPC with human-like trajectories, because what we have right now are just heuristics for the central mass trajectory. So we have to evaluate a complete, let's say we implement our control strategy using C++ and Casadi, and we solve the optimization problem using IPOpt. And in this case, IPOpt found the minimum of the optimization problem. One of the possibilities is to start from a, let's say, realistic warm start and then perform as like a sequential quadratic programming approach. And in this case, we can, in theory, speed up our computation.
That's one of the, let's say, future research direction, and this is actually the last point here. So won't start the MPC with human-like trajectories.
All right. Okay, since we are already at this place, maybe we go back to slide 72. What was not quite clear to me is what is now the role for you of the simplified footstep planner that you have? Does that initialize a solution? Does that give you some constraints, or what does that do for your MPC?
Okay, yeah. So the footstep planner generates the nominal footsteps. So we use them inside the cost function of the MPC. So footstep position and timings.
Why?
So
Why do you do that?
Because our MPC doesn't automatically generate the position of the footsteps. So in order to have it online, at least in this kind of structure, we start from a footstep planner, high-level footstep planner that, for instance, can use also vision in order to sample the footstep position given the environment, and then the MPC try to, let's say, run online and adjust it. Because in this case, if you want to use, for instance, vision, at least from my opinion, the thread should be, I mean, it's a complex thread because we have to, it's a complex task because we have to handle all the vision information coming from the cameras, and then we have to perform some stuff in order to generate footsteps. So the idea here was to have a high-level footstep planner and then a centroidal MPC that generates and adjusts the position of the footsteps.
So you're adjusting the foot position, which means you're optimizing for a foot position.
Exactly.
You're optimizing for a center of dynamics motion at the same time.
Exactly.
So
I have
how exactly goes this in? Is this a regularizer term that you have?
Yeah, exactly. So in the cost function, actually, I have also a slide for that. So let me, didn't show this slide, but I prepare it. Okay, so actually the objective function is this one. Okay, we have the position of the central mass that is regularized using a heuristic. And actually this kind of heuristics assumes that there is a spline passing between the center of the foot when the robot is in double support. And then we also have a regularizer for the nominal contact position. And okay, some terms regarding the average of the contact forces and the rate of change of the contact forces. So this is actually the objective function. So let's say we consider the position of the footstep, that is this one here, in the optimization problem as a regularizer. And then we look for the PCI, that is the adjusted position of the footstep or contact in general.
So what does this effectively do? If you go to the video that you showed on slide 71, you showed at the beginning you run your foothold planner.
Yeah, exactly.
And then so you get like all your nominal footholds, and then you let the system go and you disturb it.
And the robot was falling.
Yes.
While here, I push the robot, and the MPC.
Can you go to 71? Can you go to 71, please?
71.
Yes.
71. Okay, this kind of example.
Yes.
Okay.
Give me 1 second. So what we see here in red is the nominal footholds that you plan to your simplified model. Now you run your controller. You get these nominal footholds as regularizer terms into your controller, into your MPC controller. Although you're off, you're not replanning a nominal foothold, but you're getting that as a regularizer from outside, from a very old pre-planned setup. And you're doing your MPC.
I completely understand your question. So in this experiment here, that is just a simulation in Matlab, is in this way. So here we have long footstep trajectories, while so in this case, I'm not going to, let's say, regenerate again the footstep position in the nominal planner. While also in this experiment is like this because we just do the experiment for the video, and so we generate 5 footsteps. But actually, our Unicycle Planner generates trajectories online. So this means that it has an horizon. This horizon, let me go again to the video of the Unicycle Planner because it should. Okay, so this is the video of the Unicycle Planner. So the Unicycle Planner works in this way. every, I don't know, every double support phase, we ask for a new trajectory for the Unicycle Planner. And the Unicycle Planner consider the position of the two step to replan the new trajectories. Okay, so in this case, applying this architecture, applying our centroidal MPC into a 3D control architecture, we will be able also to regenerate the trajectory generated by the Unicycle Planner. So every double support in the end.
Good, thanks a lot. Let me switch gears before handing over to Jerry. Another part of your thesis deals a lot with modeling of flexibilities, both in contact and the link dynamics. So let me start with the contact. Do you have any understanding of how much these errors that you have in not knowing how compliant the environment is in comparison to the actual errors that you have in your models of your complete robot? How much of that is? Is that like a really significant contribution to it? Or is this very little? On the not in simulation, I mean, there you have a perfect model,
okay,
but on
so
the real
actually,
physical system.
Okay, so I didn't present this part in the presentation because it's actually an ongoing work and is not completed. We try to identify the contact parameters on a real scenario. So what we try to do is to put the robot on the surface, a compliant surface, with one foot on a rigid floor and the other foot on the compliant surface. And there we try to identify the contact parameters. In order to do that, we actually had some problems with unfortunately, with the hardware. And this is the reason why I didn't present it in this presentation. This is mainly due to the value of the force torque sensors and their calibration. So actually, we didn't try again yet the controller on a real scenario. So I actually cannot completely answer your question because we didn't actually. I mean, one of the main problems of ICAP, is controlling the robot in torque, also on stiff terrain. As I mentioned before, because ICAB doesn't have joint torque sensors, and we estimate the joint torque using actually a recursive Newtonian approach. And this means that all the noise of all the sensors plays a crucial role in the estimation. And actually, as a future direction of another PhD student is to improve the estimation of the torque of the joint torques in order to have a better closed loop in the low level.
But I mean, one thing is the force measurements, but the other thing is that what you're presenting here requires an extremely precise state estimation. You have to measure the deflection of the ground contact, which comes through a state estimator of a body on a compliant surface, whereby the state estimator itself typically makes assumption about the environment. Is it feasible to run something like this ever on an actual physical system? Because you're talking about centimeter or like millimeter precision that we need to have a proper contact.
I completely see your point. It's a super interesting question, and actually, I think it will be super complex. Okay, I want to tell you the truth. I don't think that we are going to deploy this controller on the real robot and then we are super sure that it will work forever. But I think that we're hopefully able to reach some results tuning a lot the controller. So actually the direction here was mainly related to so we start from the modeling of the contact, doing in a different way from what the state of the art in general does. And then attaching this kind of architecture on the real robot, I think it will be really complex. Of course, regarding the deflection, we need.
Can I shortcut this for a second?
Sorry.
Yes.
Okay, so regarding
did you ever run the simulation with a state estimator?
Okay. No, actually, yes. So the simulate.
No, but the state estimator, it doesn't take the simulated base, but like measures joint measurements and contacts and does estimate the state. Did you do that?
Actually, we perform our own simulation, so we design our simulator. And here,
so where does
we close the loop.
Where does the floating base position
and motion come from? That's true. So we assume that we can directly control the torque, and the floating base is given by sort of ground truth. We don't have any kind of floating base estimator here, and low-level joint torque control.
Okay, thanks. I'm handing over to Jerry.
All right, thanks, Marco. Hey, thanks, Giulio. That was great. Excellent work. Excellent presentation. It was very clear. Let's see here. So first question is, so you said that you need force control in order to do the viscoelastic surfaces or elastic links. Why is that? Is there any fundamental reason why a position control robot couldn't implement your algorithm?
Okay, yeah. So you mean for this work regarding the compliance? Okay, let me go to the. Okay. Here. So actually, in theory, it's possible because if we assume that we don't want to close the loop on the counter forces, we can go 1 degree of derivative low. And so in this case, instead of having the acceleration here, we will have the velocity. And here, instead of having the contact force rate of change, we will have the, let's say, the force, directly the force. One of the main problems here is the fact that the force depends non-linearly with respect to the velocity of the foot. So this means that it is a bit more complex. So if this kind of system is not, let's say, standard dynamical system in control form, nonlinear control form. And so having a nonlinear dependency here may be complex. Of course, it can be something that can be done. And yeah, so in theory, yes. In theory, yes. So going here again, yes. We should just to decrease the degree of derivative of all the terms here.
Okay, so you think it could possibly be possible?
Yes, still there are all the problems that Professor Utter mentioned before. So having a reliable floating-based estimator and measure, yeah, this is the main problems. Okay.
All right, cool. So you assume that you had the 0 moment point or center of pressure in the middle of the foot in your planner and everything. What's your thoughts on having to actually like move to the front of the toes like in human walking?
Yeah.
During the stride.
Yeah, actually, yeah, this is yet another, let's say, future development. What we have right now is a planner that Dafarra, that is actually a postdoc here, back in time developed. And I start from this considering a constant ZMP inside the support polygon during single support. But of course, this can be done. But in order to, let's say, solve this question, we decide to move from simplified model to the centroidal model. So actually, in the centroidal model, the contact forces, the ZMP will move during when the robot is in single support, because the outcome of the MPC are the contact forces and the contact range during of the foot. So of course, the ZMP will move during single support.
Yeah, it's moving for control, but your planner, if everything.
No, yeah, actually, yeah, there the planner doesn't consider at all the ZMP. Yeah. For the simplified model control strategy, yes, and this is constant as a future direction. We may thinking to have the heel toe motion actually, so the movement from the heel to the toe for the ZMP.
Yeah. Okay. Cool. Yeah, and then also maybe to get human looking walking, you kind of
this should improve exactly.
Yeah. Okay. So you talked about modeling flexibility and compensating for it. What about backlash? Any thoughts on that?
Yeah. Okay, on Talos, actually, they didn't notice any kind of backlash. On ICAP, actually, there is small backlash on some joints, but at least the controller that we use are tuned such a way this backlash doesn't, let's say, damage or doesn't, I mean, it allows still the robot to walk. And so while on Talos, the backlash seems to be not there. So yeah, I didn't think about that part while developing that part of the research. Of course, the backlash plays an important role, may play an important role. And in this case, we may try to model it somehow and try to consider it in the controller. Or another hypothesis is to assume that the backlash is just a sort of disturbance in the input of our system, and we may try to design robust controller that consider this in one of the assumptions of in order to consider to generate the joint torques.
Okay. Can you go to slide 13?
13, yes. Yeah. Let me move this.
Sorry, 13.
13, sorry, not 30. Yeah, 30. Yeah. Yes.
So the equation 3, shouldn't that be x dot dcm, not x dot com? Or am I getting this?
So here, yeah, so I actually use the nomenclature that is used in Engelsberger. And then in this paper is also, there is a comparison between the DCM and the instantaneous capture point that in the end, even if let's say the reason why those two models has been developed is different, because the capture point is the point on the ground such that the robot has to step in order to stop.
Yeah, no, I'm just saying that. I'm just wondering, is there a typo in 3? Shouldn't it be DCM dot equals 1 over B DCM minus center pressure? Or I guess maybe that.
This one. You mean this one?
Yeah. Oh, okay, I guess 3 leads to 4. Oh, sorry, that's the stable dynamics. Duh. Okay.
Yeah, that's the stable dynamics. Yeah. This one is the stable dynamics.
Okay. I got it. Sorry. All right. What's your thoughts on you've got a 3-stage hierarchical control. What's your thoughts on being able to combine it all into like one stage with one big model predictive controller?
Yeah. It would be really nice actually, and there are several work doing that. There is a lot of papers that has been written by the group of Geppetto group of Olivier Stas, where they try to merge all together in a whole body controller. We also try to do that, so whole body MPC controller, but at least our experience is that it's not easy to have this kind of architecture running online. And moreover, it's complex to tune it, because simplified models in the end are linear models. Okay, and so finding the gains of a linear model for a controller is way simpler than tune a nonlinear model predictive controller. But of course, it's one of possible direction. And actually, we try to go in the middle also here, because instead of using whole body controllers, we want to, no, it's not this one slide, but we want to consider the human-like motion that has been generated using, okay, this one here. So in this work here, actually, Vishekonte 2022, the motion of the human are generated by a neural network, and then we can directly remove the, let's say, the two-step planner, and we can directly generate the centroidal MPC. We can directly implement the centroidal MPC and then send the commands to the robot. Implementing all the stuff in a unique MPC controller, I think it's still really hard to have it online and adjust also the position of the footsteps online. It's really hard.
Okay, cool. One last question. Let's see here. So with the real experiments on the compliant surface, saying that you weren't able to do it with iCub yet, do you think you could like just kind of test your theory and see if you can do good enough state estimation with like a single leg or some 1 degree of freedom system, just a simple setup so you don't have all the complexity of the full robot?
Yeah, so regarding the model, yes. So that one actually is a work that is ongoing. And so regarding the validation of the model, yes, of course. Regarding the entire controller, we need the robot. So yes, it's a work that is ongoing, actually, this one.
Okay, cool. All right, well, that was the questions I had. Thanks.
Thank you very much.
Okay, so we thank a lot the reviewers. And now we move to the jury members. Alphabetical order. So Johannes Berger.
Can you hear me?
Yes.
Perfect. Giulio, thanks very much for the talk. It was very, very nice. I also had a look to the thesis. Beautiful. Thanks so much. So,
Thank you.
now
Thank
a
you.
few questions.
Yeah.
Like you showed in one of your sets of experiments that the instantaneous controllers outperformed the MPC controller. Do you have a reasoning for that?
Okay.
Like,
Yeah.
Why could that be?
So yeah. So actually, we noticed that I think it is mainly related to the cost function that we use. So the MPC controller that we implement here try to regularize the rate of change of the ZMP. And so it seems that is more, let's say, subject and sensitive to errors on the central mass tracking. At least we noticed this during the experiments. And that's the reason why we were not able to increase the velocity, because as you can imagine, as soon as you increase the velocities, also the low-level joint position tracking plays a role there, no? Because of course the error will increase, and so in the end the central mass error will increase. And the MPC seems to, let's say, not be fast enough to, and I mean fast enough, I mean given the cost function that we use, to perform the same, let's say, outputs of the instantaneous controller. Yeah, so this one is the main reason why.
Yeah. Can I just quickly ask, like the MPC does not track, like not try to track or not track. Like, is the MPC built around the concept of DCM, or is it like?
Yeah, the MPC considered as a prediction model the DCM. So here is the prediction model.
But the ZMP
so
rate
the output
is
of the
an additional constraint or objective, like to have a low ZMP rate, I guess. Is that it?
No, sorry, yeah.
Having a low, a slowly changing ZMP is one of the additional objectives, I guess.
Yeah, exactly. Yeah. So there are two objectives. One is the DCM tracking.
Yeah.
That has been, let's say, the planner is the one that actually you presented back in time. And then there is another task for the regularization of the rate of change of the ZMP. So I think is the main problem here is the fact that tuning those kind of tasks may be not simple. So a possibility is to also generate a desired ZMP trajectory and regularize the MPC along this kind of trajectory instead of minimizing the rate of change of the ZMP. And this may help the, let's say, improving the overall performances.
Good. Thank you very much. That was question one. Question two was basically the one that Marco already covered and Jerry also had in mind, like this ground truth versus like these flexibility estimators. Like, so I'll ask a somewhat similar question. So like I had that question too, but like that was already asked. Yeah, you have the contact model and that's fed into the whole body controller. Like, how robust, I'm not quite sure if you examined that, how robust is your whole body controller to an imperfect model of, maybe it's the same model, but different parameters? Like,
yeah, actually, I have a slide for this specific question.
Yeah.
And in the, let me look for the slide. Okay, so, okay, this experiment is done only in simulation. Okay, so we have this our simulator, and in order to, let's say, try to understand how robust is our controller in case of parametric uncertainty in the contact model, we try to run this simulation. So here, the measured contact force is affected by a white Gaussian noise.
Yeah.
And then in both on the paper and on the chapter of the thesis, there is the analysis with different values of covariances. And there is a value of the covariance such that the force, the MPC is not, sorry, the controller is not able to anymore to guarantee the balancing.
Yeah.
But still, okay, this is the only in simulation, but it's a way to try to understand the robustness capabilities of the controller.
Yeah. So to some extent, it is robust, I guess.
Yeah, at least in simulation for this kind of noise.
I have a very specific question that
Okay.
is related to my one of my long-term, how to say, like targets, but that I myself never solved with it. What would happen if you lift the robot up, like using the crane or whatever, lift it up? Would the controller go unstable?
Yeah. So in torque, yes, because we try to let's say one of the output of the torque control scheme is the counter forces. So when we try to lift on the robot up, the foot doesn't touch anymore the ground, and then it tries to move as fast as it can down.
Yeah.
So yeah.
Basically, the contact model is then very wrong. Yeah.
Exactly. Yeah. That's the yes.
Okay, perfect. Then you presented the, I guess, task space inverse dynamics compliant and one flexible. Could you consider combining the two in the compliant and flexible?
Yes,
model?
in theory, yes. Since actually, actually a compliant environment can be seen as a sort of flexible link somehow, no? Because we can imagine the soul of the robot, an extension of the soul of the robot to part of the environment.
Yeah.
And so in the end, it would be possible to merge the two ideas together and design a controller for flexibility in general. Also exploiting this kind of consideration.
Thank you. Next, your nonlinear MPC.
Yes.
Yeah, exactly. Like one typical problem I'm aware of that I don't work myself on, but like you have okay. How do you limit the angular momentum basically?
Okay.
The let's say the integral over change in angular momentum, and how is this related to maybe a postural limitation of the robot? How could that maybe?
No, I completely understood the question. So regarding this central MPC, we try to minimize the angular momentum. So one of the main ideas is to remove this kind of minimization and use this human light trajectory motion generator to compute the desired, let's say, sort of reference, even if it's not feasible, but it's a reference that makes sense for the angular momentum using the desired quantities coming from this network, along with the centroidal momentum matrix, because then we can compute the angular momentum. And this can be also considered here. Let me go back to this slide. Okay, here we can remove the angular momentum minimization and add a term that try to regularize it using this kind of trajectory. Right now, this is the implementation, so we minimize it. We try to minimize it.
Yeah. This is like with regard to a reference where here the reference is 0 and like another reference might be non-zero. What I'm also pointing at is like when you push the robot, let's say hard.
Yeah, having a reference equal to 0 is would be not the right solution here, also because it tries to keep, the angular momentum equal to 0, and so it will move the arms a lot in order to counteract the error.
Yeah.
And also, it may be possible that when you walk at high velocity, having an angular momentum equal to 0 may have may generate strain motion on the robot.
It may very much, I know. Okay. Then, like two follow-up questions to the nonlinear MPC. One is like in your introductory slide, you showed like non-coplanar surfaces and multiple limbs in contact, or multiple end effectors in contact. In the I don't know, the simulations you showed later, you had like coplanar and let's say bipedal only. Like we're limiting your work or the scope of your work to like bipedal in the end?
Actually, okay, with this kind of controller for the MPC, no.
Yeah.
So in theory, it can be used. We deploy on the robot on the architecture that we have right now that is, consider just two contacts that are the fit. We are, in the future, we would like to extend the architecture to multi-contact, so also the whole body controller to multi-contact scenarios. But the MPC itself is already ready, let's say, for handling multiple contact, because the very same implementation can be used for one leg system and two leg systems. So, and also in theory, also with parapet. So, okay, then the experiments on the robot has been done with the architecture that we have, and we rely on, and so. Yes, but in theory, the MPC can generate multiple kind of content.
The final one with regard to this nonlinear MPC, I'm not quite sure if, like in the simulations, but in the experiments we saw, I didn't see a whole lot of like angular momentum being generated. Did you try to regularize it, like kind of as much as possible?
Yeah. So actually, here the weight on the angular momentum is pretty high.
That would prefer.
So this is the reason why you. Yes, that's the main reason why.
Then, regarding your overseas or the time at last, did you guys try any experiments, like any experiments using your controller, like even maybe just standing or even like walking?
Sorry, which kind of?
Like, if you guys tried your controller on the real Talos.
On the real Talos, actually, okay, this is actually no. Unfortunately, in the period that I went there for the secondment, when I was ready to test the stuff on the robot, due to the COVID pandemic, I was forced to stay at home. So this is one of the reasons why, but actually we are planning to deploy it. More than the controller, the estimator, because the estimator that they have right now assumes they compute the joint torque estimation using the information coming from the nearest joint, while what I implemented, and then is more detailed in the thesis, is a complete recursive Newton-Euler algorithm. So we consider also the force acting on the system and the measured joint torques. So actually, they are interested on this part.
Very nice. Do you are you aware of like the main problems? Like I guess the main problem I hear are these flexible links. So maybe like pretty flexible. Like if I don't know if you touched the robot, if you can like really shake the legs when it's meant
actually
to be
okay, no, the flexibility plays a crucial role while start walking at highest velocity. So when the robot is balancing, actually the flexibility, we can use a standard controller, so standard task-based inverse dynamics or momentum-based controller for balancing. While increasing the walking velocity, they notice that this flexibility is giving some problems for the locomotion.
Do you think the problems is more in like vibrations, so somewhat higher frequency, or more in, let's say,
more on the tracking, actually, more on
the foot tracking also?
Yeah, exactly. Exactly.
Okay. Yeah, very interesting. And one final question. I'm really not sure if you had a look at that at all. Well, I think you had a look at it because you were referring to my colleague's Messerschan's work, like this mattress walking and so. Did you have a look, or do you have an opinion on like this passivity-based whole body controls versus inverse dynamics?
So actually, passivity-based controller are really nice. I have to tell you the truth, because instead of modeling instead of trying to model as much as we can the environment, we give the controller the possibility to be robust somehow. And sometimes modeling could be not the right choice, because it makes more complex the controller, and then we have to identify parameters. While having a passivity-based controller may really help. Also, I think on ICAB, so having a controller that consider an error tracking on the joint torques, because we know that we have it. It could be probably a possible future direction in order to improve the high-level torque controller on the robot. because what we have right now assumes that the torque that you require is the one that you get from the robot. But on ICAP, this one is not in this way, at least.
Good.
For
Thank you very
locomotion.
So that was all my questions. Thank you very much.
You're welcome. Thank you.
Okay, so now we move to Professor Alexandre Danessa.
Thank you, Daniele, and thank you, Giulio, for the nice presentation and the great work you have done. So the nice things about going last is that most of the questions have been asked, right? So I get the easy job kind of thing. So I have just a couple of more personal curiosity than actual questions, and just some understanding of your ideas. So let me look at my notes here. So first of all, in one of the videos that you showed, actually several of the videos, when ICAP walks, it looks like he's swinging both arms parallel, independently from which foot goes forward. Usually, when you move forward the right foot, you go forward with the left hand, right? So you have that kind of marching kind of behavior kind of thing. But I noticed that ICAP, when he walks, actually moves both arms forward. I was wondering if the way you model it, you have only 1 degree. I mean, you control the two arms at the same time on the whole body controller, or why would that be the case?
Okay. So first of all, we don't have any, when the robot is controlling position, okay, we don't try to regularize the angular momentum. So this could be one of the reasons why we don't have this wing motion of the robot arms. In the controller, we just regularize the joint position, and we have a task for the torso orientation. So the torso is kept parallel to the walking direction, and so that's probably the reason why we don't have this kind of motion that you are referring to.
Okay, well, there was a video that was later on. It was unfortunately there was no number on the slide, but it was close to the late 40s. It was before 51, because I have a note on 51, and the video was before 51. I don't know which.
Okay, this one probably.
Yeah, perhaps. Yeah, perhaps. Yeah, it was the simulation. Can you run that video? Let me see if it was this one.
Okay, so also here, there is a task for the angular momentum, but this task is generated from the inverse kinematics above. So the inverse kinematics that I show you for actually the one that we use for running the experiments on the real robot has been run for, say, in case of stiff terrain, and then we use it as a trajectory reference for the angular momentum. So also here, we don't try to minimize the angular momentum, and the angular momentum that is generated is the one that generates the motion of the robot in position. So that's the reason why we don't have that kind of motion.
Okay, sounds good. I mean, it looked like the two arms were going up together, so I was wondering why that was the case. I guess it's
actually,
just,
I think this is just the output of the controller, but we don't have any kind of task that does this motion. Not at all.
So why are you even controlling the arms, though? I mean, at this point, why don't you just leave them down the body and don't move them if you're not using in the optimization?
So you mean keep the arm outside from the control strategy, so keep them constant. Well, okay. So listening this question after what you mentioned before would give me to say yes, you're right. But actually, removing the arms is, from the control strategy, in our opinion, is not the right direction. And I would like to explain you. I mean, we use this kind of controller for, let me go here, for telex-systems. And in telex-systems, the controller is only one, that is the working controller, and we want to control the position of the arm of the robot. So, and this actually, the controller that runs on the ICAP here is the one that I presented at the beginning of the presentation. So it's part of this thesis. So this means that if we remove the arms from the control strategy, we are not able to, let's say, also perform telex-systems and teleoperation. That is actually one of the goals of our research line, I would say.
Okay. Now that makes sense, but although you know, that is like
no, okay,
it's a different task, but at the same time, understand.
No, but
and I wouldn't
completely
suggest to take the
understand.
arms out. I mean, absolutely. I mean, you have the arms; those are extra degree of freedom that you can use to stabilize the angular momentum.
Exactly.
Perhaps I would just, since you have them in the controller, I would just add extra task in your optimization to use the arms more effectively, rather than remove them. I mean, I wasn't suggesting that you should remove them. Okay.
Okay.
No,
Thank you very much for the suggestion.
That answers my question, absolutely. So let me see. Now, I was looking at the thesis, and actually, I'm very interested. So on slide 51, that's why I knew that was not before 51. On slide 51, and I looked at the thesis, and I couldn't find an actual definition. What is the physical meaning of a flexible joint state? What is S? What does S mean?
S is the positions. Okay, in the thesis, I think is at the beginning of the thesis. There is when I present the, let's say the robot modeling. I in general use with S. The S means the position of the joint. S dot is the velocity of the joint, and with Q in the end is a sort of list that contains the position of the base, the rotation of the base, and S, that is the position of the joints. In this case, is the flexible and the actuated joints, but is exactly the same. And then the derivative
sorry,
is not
I misunderstood. I thought that SF was a particular state that was capturing the flexibility
no, it's the position,
of the joint.
It's the position.
It's just the position of the flexible joint. Okay, I got you now.
Exactly.
Okay.
Exactly.
Yeah, that's why I was trying to understand what it was. Okay, I understand now. Thank you. So let me see. Now, I have more of a conceptual question, right? Oh, actually, before I ask you my conceptual question, I have another more specific. So on slide 38, you talk about how you use the rate of change of the contact forces for your modeling purposes. And it's somewhere in there. Yeah, subject to contact forces rate of change.
Okay, yeah, this one.
When you minimize with respect to FK dot, right? I was a little bit raising my eyebrow because rate of change of contact forces is a pretty difficult variable to work with. I mean, it's you mentioned yourself how you're dealing with spikes, and different modeling assumptions can produce you very different spikes, as you know, right? I mean, you just include a little bit of compliance, a little bit of soft terrain, or a little bit compliance in the joints, and the rate of change of the forces at contact, you know, it can change a lot by order of magnitudes, really. So, I mean, I was just trying to understand why did you choose to work with the rate of change of the contact force? I mean, I just think that is a little bit dangerous.
Okay, no, yes, I completely agree with you if we are going to measure it, but in this case, it's the output of the controller. And I decided to use F, so the rate of change, because the model that we propose, since we want to design a controller that generates torques, actually here we have the measure torques, the measure contact wrenches that are generated by the flexibility of the ground. So in order to control and moreover, these estimated contact wrench, let me go on these other slides, depends on the position and velocity of the rigid body. So for instance, the foot. So it's not possible to, in order to, let's say, control the force, we should require to directly control for instance, the velocity. But in a torque control strategy, what you can change is the acceleration. So if we say compute the time derivative of these, it will have some terms that depends on the acceleration. That is actually the linear acceleration and the angular acceleration, and those are, let's say, considered inside the optimization problem. So I don't know if I answer my question, but in the end, FK dot depends on, it's a nonlinear system where V dot is the acceleration of the foot. Here, in this case, yes, is the acceleration of the foot.
So, Giulio, just to make sure I understand, so you optimize with respect to, well, no, with respect. I mean, you use fk dot as your optimization variable.
Exactly.
So you,
exactly.
out of the process, you come up with a desired rate of change of the contact forces, and then you use the acceleration to track that desired value. Is that correct?
Exactly.
Okay.
Exactly. So here, so this is the slide that should explain this. So here we have estimated, so measured or estimated, and the optimization problem generates a desired robot acceleration that then is plugged in the joint dynamics of the system, and we send the torque to the simulation.
Okay, that makes sense. Okay, so now my conceptual question instead, right? And it's just because everybody else asks you about your modeling of flexible joints, and so I think I need to ask you something about that too, right? Otherwise, it doesn't look good. But my question is the following: I was a little bit surprised to see that you had, quite different approaches between modeling soft terrains, so compliance in the terrains, and then compliance in the links, right? I mean, from a behavior point of view, a robot that walks on soft terrain and a robot that walks on a rigid terrain with the flexible links are subject. I mean, of course, the dynamics are different, but the challenges are similar, right? Due to the flexibility of the terrain of the links, the center of mass is gonna shift with respect to what you think is gonna be, and so the whole control is gonna be affected by that kind of uncertainty. And so I was wondering, in your opinion, do you think that you could find an approach where you can handle flexible joints and flexible soft terrains, at the same time? I mean, in a similar approach, having an approach that can handle both at the same time, rather than have two such different approaches for the two different cases. And this is, I mean, I just want to know what you think. I mean, there is no right or wrong answer.
Yeah.
Just what's your opinion?
Yeah. So, in theory, yes, because this model here, instead of having, let's say, the ground and one of the rigid body of the link, it can be a cross section, between two links. So in this case, we may have a deformation of the link in this way. What I did during my period there in Toulouse, we was starting from an already given, let's say, model. And so that one was the starting point, mainly. But in theory, this one could be really a nice research direction, because thanks to that, we can also, move from the assumption that a flexible link is modeled with a set of flexible joints that I'm going to that slide. Because right now what we are doing is we have a flexible link, and then we say, okay, this flexible link can be substituted with a set of flexible joints. But applying the very same approach, actually, we can avoid to add this kind of flexible joints. And then we can have we can try to model directly the deformation of the link itself on a planar section. At least on Talos, this is the case, because the flexibility is just inside the cross section between the root link and the torso. Sorry, the root link and the hip. So because in that part, the link, the size of the link reduces, and then the weight of the robot makes the link deflect. So in theory, yes, and actually it's a really nice research direction. This one.
Okay. I was just curious. So
Mm-hmm.
thank you very much again, Giulio. Very nice work.
Thank you.
Daniele, I'm done. I'm happy.
Thank you, Alex. So we might open a second round of questions if there is any additional comment or question or curiosity that arose during the question time. So in the case the jury members would like to ask, this is I think the right moment for that second round of questions.
I would have one more question, if that's fine. In your like surface integral based contact model, as I understand.
Mm-hmm.
Like basically, I understood that you have like an anchor foot location with respect to which you express your potential, right? what happens if you like basically you like how to say you penetrate the ground at this anchor position and then well apply forces or like have resulting forces with regard to that. But the only way I believe you can leave the ground without having a jump in the contact forces is by passing back through this contact location. So do you observe jumps in the estimated contact force like when removing the foot from the floor?
Okay, yeah. Actually, we handle it. So inside the controller, we have a task for the, let's say, regularization terms for the contact force that is an heuristic. So this heuristic means that when the robot is on one foot, on Fz, because this regularization term is on Fz, the force is the mg. And during single support, we move from the maximum force to lower force. So tuning the gains allow us to reach the detached phase, so from switching from double to single support, in which Fz is almost equal to 0. And having Fz almost equal to 0 means that in order to satisfy the friction coefficient, the friction cone constraints, also Fx and Fy, so the tangential force, are almost equal to 0, and the torque is almost equal to 0. So this is so we handle it in this way.
Okay, so I understand that the whole body controller basically ensures that you pass.
The contact model assumes that the contact model assumes that let's say the entire surface is in contact with the environment. So currently it doesn't. We did it in order to have a model that can easily run online, because we compute offline the integral and then we evaluate it online in real time. Of course, it would be nice to estimate the contact surface, but then this opens another question: how to estimate the contact surface? On iCap, there is the skin under the foot, so we can actually mount a skin under the foot. But still, it's yet another problem in estimation. So
thanks. You answered very, very well. Thank you very much. That's all.
Thank you.
Okay, so I don't know. Thank you, Dr. Engelsberger. So I don't know if there is any other question coming up from the jury member. Okay, that's great. So at this point, we move to the other link, where we basically have to write the report, and then we come back here for the final words. Okay. Okay. Better to be together peaceful.
Okay. Thanks, Giulio.
Thank you. Thank you very much.
Yeah. Okay. So I think we are all here, and so Professor Marco Utter has been elected as president of the jury, and Jerry Pratt as secretariat. So I leave the word to Marco Utter to pronounce the final judgment.
Thanks a lot. Yeah, Giulio, it's my great pleasure to give you a warm congratulations from the whole commission. The research presented in this thesis is very original. The methods used are advanced. The results are interesting, and they were analyzed with excellent critical thinking skills. The candidates showed an excellent level of knowledge related to issues approaching during the discussion. The commission unanimously judged excellent the work undertaken and decided to award you with the title Doctor of Philosophy in Bioengineering for Robotics. So big congrats from all of us. Sorry for the formality, but that's the text I was told to be reading.
Sorry, there was some excitement in the room.
Thank you. Thank you very much.
Okay, so at this point, I think we can take a picture with the jury members, and I don't know if we have, yes, and so that we have this moment. So you can stay on the side. Whoever wants to join. So this is the picture moment. Okay, done? Yeah. Okay. So thank you very much, all the jury members, for having the time to review our work. We wish you all the best, and in the case you pass by, you are more than welcome to visit our lab. So thank you all once again.
Thank you very much.
Thank you and congratulations.
Congrats. Yeah.
Take care.
Bye.
Bye-bye.
Bye. Thank you.